The year was 2022 when a United Nations report surprised many. It revealed that the world is heading towards serious sand scarcity. But sand is the most abundant material on Earth. From riverine areas to dry deserts, you can find sand anywhere. How is it possible that the sand reserves start dwindling? Interestingly, sand is also the most extracted material on Earth. Annually, around 50 billion tons of sand are extracted worldwide. And this extracted sand is used for construction alone. Sand has more than 20 types, and in terms of colors, it can be white, black, pink, red-orange, white-gray, or light brown. Desert sand is largely useless. The sand we need is the more angular type. This type of sand is found in riverbeds, banks, and floodplains, lakes, and coastal lines. The issue is the useful sand is limited in quantity. Other than construction, it is used for making silicon chips, glass products, toothpaste, wall paint, windshields, and almost every other product without which a modern way of life is impossible. One of the most important types of sand is silica. It is used in almost every glass-making product and primarily occurs in the form of quartz. You can transform silica into float glass, glass bottles and jars, and even optical fibers. Now, scientists have found an interesting way to record a tremendous amount of data on a silica glass disk. Silica constitutes 59% of the mass of the Earth's crust. Its extraction starts with blasting explosives. Wheel loaders then collect the blasted sandstone, and dump trucks transport it to the crusher line. There, the crushers crush it to achieve the desired particle size distribution. This is the McClanahan jaw crusher, used as a primary crusher for sandstone. It consists of two opposing jaw dies that form a V-shaped cavity known as the crusher chamber. The material is compressed between two jaw dies, one moving and one fixed. The discharge opening determines the intended product or yield. Typically, a jaw crusher reduces the mined ore to around 1 inch in size. In a similar way, sandstone falls on the high-speed rotor drum of the impact crusher, breaking upon impact. As the material passes through the crusher, it comes into contact with a series of anvils, or curtains, which further crush it. The crushed sand is still not pure silica. It should be graded and cleansed. For this reason, CDE Group, a well-known manufacturer of wet processing solutions, built the Silica Sand Wash Plant, which can generate 220 tons of glass sand per hour. The operation begins with dump trucks unloading crushed silica directly into the feeding system. This mechanism controls the input into the wash plant. The sand is then pre-screened to eliminate any large particles using a primary cut of 7 mesh. The term mesh describes the number of pores per inch. For example, the 5 infinite high-frequency infinite screens cut sand at 30 mesh, which means there are 30 holes on each inch of the screen. Only sand particles of a specific size can pass through these openings when vibrated. This method separates coarse sand and stores it for use in building. The purified silica sand now has to pass through attrition cells. These cells clean the surface of particulates, eliminating contaminants, impurities, and pollutants. The process includes eliminating clay slime and washing surfaces of soft or conglomerate contaminants. Likewise, the spirals remove heavy metal impurities. Gravity and the spiral chute's design cause the slurry to revolve. Due to centrifugal force, the spiral motion tends to push heavier particles inward. Separator gates with varying radii are put at the spiral's bottom. They simply direct the slurry containing the heaviest metal into one chamber and the filtered silica into another. Next, the wet, high-intensity magnetic separators separate silica from ferromagnetic materials by attracting them with their magnetic fields. The feed next enters the hydrocyclone, where centrifugal forces drive heavier substances out, leaving concentrated particles behind. The vortex finder causes a swirling motion, and fluid exits at the overflow, while solids exit at the bottom. Throughout the process, the AquaCycle thickener optimizes water consumption by recycling 90% of it, decreasing waste and environmental effect. This comprehensive process allows the effective production and utilization of silica for a wide range of industrial applications. Silica mesh sizes ranging from 30 to 70 are considered excellent for glass making. There are two popular techniques of manufacturing glass: float glass processing and glass blowing. The float glass process involves floating molten glass on a bed of molten tin to achieve a consistent thickness and smooth surface. On the other hand, the glass blowing procedure involves blowing air into molten glass to mold it into the desired shape. However, in order to make glass, silica must first be melted at a high temperature. Tons of extracted and purified silica are sent to the batch house for this purpose. A batch house is a facility where silica and other essential chemicals are evaluated. They may contain soda, lime, and aluminum. Soda reduces the melting point of glass compounds, lime increases their stability, and aluminum strengthens them. These materials are then uniformly blended in a predetermined quantity to produce a certain type of glass. Broken glass can be utilized in the production of float glass. Cullet recycling refers to the process of recycling discarded glass. It is also blended with batched material, saving up to 15% on fresh raw material. Next, the fully batched material is put into a huge furnace. It melts the glass material at temperatures as high as 3000 Fahrenheit, transforming it into a several-foot-deep pool of liquid glass after about 36 hours. In a separate area, this liquid glass is placed over molten tin heated to 2000 degrees Fahrenheit. The bottom of the glass floats onto the tin in the tin bath and is heated from above to make a continuous strip of glass, often known as a glass ribbon. The method is known as the tin bath. To assure the quality of the glass, the manager and his team supervise each procedure from the control room. The created glass will next undergo an additional procedure known as annealing. Layer is a long, tunnel-like furnace with separate oven portions. There, the glass ribbon is gradually cooled before passing through a pair of water-cooled shaping wheels to achieve a consistent thickness. At the end of the layer, the manufactured glass is pummeled with air, further lowering its temperature until it is ready to be cut. Cardinal FG Company in the United States manufactures 600 tons of float glass per day. From the main furnace to the cold end, they produce 20 miles of glass ribbon and use cutting-edge technology to ensure that their output is flawless. Cameras identify uniformity in the glass. Lasers highlight any irregularities along the glass's edge, and professionals do human examination. If any imperfection is found, that section of the glass ribbon is automatically marked and then cut away. The XY cutter is a specific equipment that creates a tiny, continuous scratch on the glass surface from one end to the other edge. This method, known as scoring, provides controlled glass fracture along specified lines. During a bump roll, the scored ribbon splits apart or is divided into smaller glass sheets. The edges are then trimmed. If the glass edge remains untrimmed anyplace, the laser technology identifies this flaw. The faulty sheet is sent to the batch house for recycling. Finally, the ready glass reaches the packaging station. The orders are carefully packaged, wrapped, and labeled. Float glass production processes can only provide glass in the form of flat sheets. The air is blasted from the inside to shape the glass into bottles, jars, or any other shape. This is why it's known as the glass blowing method. More or less, the batch mixing and melting of glass in the main furnace are similar to what we have seen in float glass manufacture. The difference in the procedure begins with the glass forming step. During this operation, molten glass is fed into thin channels called feeders. Specific quantities of molten glass are permitted to drip through an aperture at the bottom of the feeder. This descending molten glass is called a glass gob, and it is poured into a black mold. Due to its molten condition, the gob adapts to create the bottle's neck. Next, pressurized air is pushed into the molten gob to shape it according to the mold. This first form of the bottle is referred to as parison. Next, the parison is turned upright to get the required form. The addition of extra air completely defines the shape. This method of glass formation is known as the blow and blow method. It is appropriate for bottles with narrow neck such as those used to store drinks and fragrances. The press and blow process is widely used in the industry for wide-mouth glass vases. The molten gob is deposited into a black mold, but plungers push the blank form before blowing from below. This motion causes the parison, or early stage, of a glass jar. The parison is then transferred to another mold known as a blow mold. There, pressurized air is blasted to give them their final form. Glass bottles are not yet completed. They need to be annealed. For this aim, they are gradually warmed and then left for cooling. To assure the quality of the finished product, each glass bottle is tested using an automatic check system or by trained people. Everything is tested one by one, including the glass bottle's split finish and wall thickness. Any failed containers are immediately removed from the production line, recycled as cullets, and used to make new glass. Interestingly, glass is the only packing material that can be completely recycled for infinite times. However, the packaging bottles must be securely wrapped prior to transportation. Every pallet is wrapped in plastic to preserve the glass containers. Since 1984, Rotel has been manufacturing glass packaging products. Every day, this company makes 700,000 bottles and jars, using 8 different manufacturing lines. This glass bottle manufacturing company has a worth of $38 billion and is expected to increase significantly in the future. However, there is another unrecognized glass product that is considerably smaller in size, but has surpassed the $8 billion worldwide market size. It records our memories and is used on a variety of devices, including smartphones, computers, and nearly every photographic equipment. This is the camera lens. An optical lens functions as the camera's eye. It catches light and directs it to the camera's sensor, defining the image's sharpness, depth of field, and overall aesthetic. Fundamentally, camera lenses are classified into 2 types: prime lenses and zoom lenses. Prime lenses have a fixed focal range, but zoom lenses are made up of many lenses that can be physically adjusted to zoom in and out. Most of our premium smartphones have zoom lenses, but they cannot slide. Instead, they easily switch to the other camera with a greater magnification. Manufacturing a single lens or a group of lenses is far more complex than producing float glass and glass bottles. It all starts with creating the right piece of optical glass. This isn't just ordinary glass. It was picked for its exceptional clarity and purity, both of which are required for precise picture capture. The glass slabs are painstakingly studied before being marked and divided into segments. The resulting material is known as glass blanks. Now it must be turned into a clear optical lens. Experts and machines collaborate to accomplish this task. They place a blank glass or glass disc on a revolving device so that a curve generator may grind it precisely. The curve generator has a diamond cutter that uses CNC technology to precisely carve out the lens. To create a blank into a convex lens, it grinds the corners small while keeping the center thick. A concave lens, on the other hand, is created by grinding from the thin center to the thick edges in one continuous motion. This is known as spherical grinding. The lens is further refined in the following stage by precision machining. The finely powdered lens is then sealed in a metal case for further processing. This process of locking is known as blocking. The lens is now ready to undergo a transformation from opaque white glass to glossy, transparent lens. To do this, companies employ liquid abrasive ingredients such as grated emery flour and prefabricated plates. This polishing technique makes the lens surface clean, transparent, and free of scratches. A small coating of pitch, wax, or coarse cloth is applied to the polishing tool before wet rouge or other mineral oxides are used as polishing agents. Glass polishing is a lengthy process that involves oscillating lenses back and forth against a revolving polisher for hours at a time. This procedure results in lenses that sparkle, have smooth surfaces, and have flawlessly curved profiles. The lenses are set up on circular racks, affectionately known as planets, and put within a vacuum chamber. Inside, an electron beam evaporates the coating ingredients. After 3 hours of obtaining this protective finish, the lenses are thoroughly washed to eliminate any residue. Each lens, whether concave or convex, is thoroughly inspected and cleaned. The stakes are significantly high, as even a single particle of dust can compromise the optical system and reduce image quality. The lens edges are then covered with black ink. This ink shields light from the edges and prevents internal reflection. The lens is now ready to be mounted in the camera's lens frame. Camera lenses are also treated with coatings for protection, anti-glare, and other applications. Chromatic aberration is a typical issue with camera lenses. It occurs when a lens fails to properly focus all colors on a single point. To reduce distortion, lens makers combine concave and convex lenses together. A technician applies optical cement to a convex lens before placing a concave lens on top. The use of pressure ensures that the cement distributes uniformly and bonds the two lenses together. This union is critical because it stabilizes the lenses inside the lens barrel, preventing any undesired movement. The lens barrel is the final element to the jigsaw. A specialist painstakingly engraves technical information on it, such as focus length and aperture size. These inscriptions are more than just ornamental. They also supply photographers with useful information, allowing them to control the lens to achieve the appropriate image. As the process progresses, the constituent components of the camera lens come together, each having a role in the overall design. The final result is a gadget that not only takes images, but also captures moments in time, allowing stories to be shared and memories to be recalled. It's a monument to the ability and passion of those who labor behind the scenes, allowing the magic of visual storytelling to develop before our eyes. The use of light and lenses to capture images is barely 2 centuries old, although numerous civilizations have used light to communicate with each other. Narinder Singh Kapani saw the magical potential of glass for the efficient use of light in transporting massive amounts of data across the world in microseconds. His published study resulted in a new breakthrough technology constructed of glass, optical fibers, and the genius himself is known as the father of fiber optics. Inventing something capable of altering the world is one thing. Beginning its mass manufacturing is another. An optical fiber is generally made up of a core and a glass tube in the middle through which light travels. Cladding protects the core. The initial stage in optical fiber production is the manufacture of solid glass tubes. It's called preform. This tube is spun on its axis and heated to around 1500 degrees Celsius. At the same time, ultra-pure chemicals are introduced into the preform, which, when heated and contaminated with glass walls, generate minute particles known as soot. These soot particles attach to the inside walls of the tube, forming a thin coating. Layer after layer, the process proceeds. This inner layer eventually becomes the core of the optical fiber. After these layers are formed, the temperature is raised while the chemical supply is lowered, resulting in a solid rod or preform. Now, the ready preform must be evaluated to determine its refractive index. The refractive index represents light's ability to bend through the glass medium. Germania raises the fiber's refractive index, whereas boron lowers it. The preform is now ready for fiber drawing, which will result in optical fibers. Upon heating at 1900 centigrade, the tip melts and gravity drags it to free fall. Following that, a narrow tube of 125 microns in diameter is drawn. A diameter gauge system using laser technology assures that every segment of the optical fiber has the same specified size. The optical fiber is next passed through dye, which provides a protective coating that makes it durable and simple to handle. It can now be coiled onto a drum. It passes various tests and trials, including tensile strength, at least 100,000 per inch, and loss of optical power, carrying capacity, and numerical aperture. Recently, scientists and engineers uncovered another secret purpose for glass. A piece of clear fused silica can record a lot of data. Furthermore, the data on the silica layers can survive for more than 300 million years. Hitachi pioneered this technique. They began working on it in 2008, and after years of effort, they successfully developed the femtosecond pulse laser apparatus. This high-output laser saves data as 2D code by inscribing dots on a layer of fused silicon. An optical microscope allows computers to read and retrieve data. Hitachi says that it can store and retrieve data over more than 100 layers of an inch-thick silicon piece. Microsoft is another corporation working to unlock the full potential of glass in data storage. The corporation launched Project Silica with the goal of encoding data on glass in the form of voxels, or three-dimensional pixels. They even built a glass library to keep these data storing glass pieces. There are specific librarian robots that will manage these crystalline archives. These were some of the marvels of glass and its products. I hope you found this documentary informative. Share your opinions in the comments, like the video, and we'll see you next time.